Hello everyone. Hello everyone. Am I live? Hello everyone. Can you see me? Am I live? Yes. Write in the chat box so that I can just know that yes. Good. I see many learners saying yes, I am live. Okay. I am audible. Audible? Yes. Yes, all fine. All good. Okay. Okay, so here we begin. Let me start with some promotions that are due. So let's just wait. So one is this one, that fast track your JEE preparation with Unacademy Super 20. Top 500 rankers stand a chance to attend a 2-day in-person camp, all expenses paid, boot camp. Other features also you can just check. These are the other features. Moving to the next one, you have got Unacademy Super 20, participate and win. There are a lot of prizes like MacBook, iPad and whatnot, right? So this is also one thing for you. Again, you have got 20 lucky participants from the test will win full set of ITJ books. That's also one of the prizes. You have ITJ Combat coming up every Sunday, of course, 11 a.m. and this is 21 questions, 60-minute test. Apart from a scholarship, you also really have to increase your knowledge, and so I believe in that way, that it's like both thing. Then, of course, you have got your race towards J22 top ranks begin. So you can have some kind of dedicated leadership batch and you can read all the features. And then class 11th boot camp, you have got this kind of thing. And this is all the thing is here. You can check that the dates are not the dates are also there. 12 to 18 December, 7 days. Correct. 38 is just this many sessions are there. So you can plan all the things and you can just check. Okay, so that's all for this one now. Then let's go to other thing. For those who join late or something, this is just something about me. So I'm Alok Kumar, your favorite educator, and you can follow me and you can check my credentials. And many of you know me also, but still. And then next, there are some lectures by me. I normally teach live at Unacademy, and my classes are going on that you can check later. Some have changed also, so you can just check those things later. Okay, so now we will begin our lesson for today, our class. So as I continue from the last one I did some identities, cyclic identities, and then I applied it in many problems. Today also we will do this thing. So now it is your simple identities or charming Olympiad problems in complex numbers, number theory, and finally an IMO problem. That also is there an IMO problem. So let me start and let us see. I have done the basics almost, and many problems last time also were really interesting, but still this session is going to be independent. I mean that those who have not done the session, they will not lose anything because I'll anyway cover all the things, right? So I will be telling you about the derivations or other things, so you need not worry. Okay, so and some new techniques also will come up. So first is that you have to simplify the following expressions. Some person Ananta is saying that complex numbers nahi aaya abhi tak. Don't worry, complex numbers, it's not really about complex number, just about some modulus thing. It's very pretty elementary. I can teach you right there. So it's not that I am going on heavy duty complex numbers. Very small idea, basically definition and what you mean by modulus. So no need to worry. Okay, now first question deals with that simplify the following expression, right? So this question can be given in any exam in the form that they may define f abc equal to something, f abc, these numbers, and then they can say that okay, just you find f1 plus root 2 and root 2, something, anything can be there, right? This kind of thing. So how do you deal this kind of thing? Any idea that how can you simplify? It looks like cyclic, but a plus b is there, a plus c is there. Last time we did all a minus b, a minus c. So what could be our approach? these kind of questions do come in ISI entrance, ISI or CMI. They have got something called part B, and then in part B you have to do these things in part B. So I think you should be fine if you are prepared for those exams. So can someone just give the hint that how we will do it? Subtracting 1. So don't say subtracting negative, subtracting 1 from each. Subtracting 1 from each, okay, but what would it achieve? Even if you subtract 1, what are you going to achieve? That's my question. Because a square might cancel. BC will not cancel, they will add up, right? You can build on that approach later, because right now time won't be there to evaluate each approach. But let me tell you what I think about it. So first of all, it is not a minus b minus c. So what I write, that I will take the LCM. So this is a plus b. I'll write b plus c, c plus a. Cyclically I'm writing. This is this. My numerator becomes a square minus bc, and times, you see, you will get b plus c plus b square minus ca. You will get c plus a. b square minus ca, and then you will get here c plus a. You will get here c plus a plus c square minus ab, and times a plus b. This is what you will get. You end up with this kind of thing, b square minus ca. Now, how do you factorize something like this? If it were b minus c, I could have applied the cyclic identities that I told you last time. Unfortunately, it is all plus. We don't have any good factorization for this. So what I do, that I have a good idea. I write this, the whole numerator, as, say, think of this as p of a. So p is a polynomial. Think of this. So p of a is a squared minus bc times b plus c plus, write out the full, b squared minus ca. Very interesting problem and quite surprising answer. So they will make good question for subjective, not for objective, because you can check always, right? So somebody can put just the values 1, 2, 3 or 2, 1, 4 or 1, 1, 0, anything you can put, right? So they will make good question for, this will make a good question for either ISI object, ISI part B, or some other exam where you really have to write answers. It also may come in part of that, in inequalities. It can be dressed up like that. Okay, so this is PA. Now look at this, what is happening. A square minus BC plus C. So if I look at it, a polynomial in A, P of A, so evaluate that as B, P of minus B, means I am putting A equal to minus B. So set A equal to minus B, set A equal to minus B. If you put A equal to minus B, is P of minus B. So wherever you see A, you put B first. So you will get here B squared minus BC, B plus C you leave, B square minus CA, so B square you leave, and you will put here CA. So wherever A is there, you will put this one. So B square plus BC. This is one thing. And then here C plus A. So you will, wherever you see this one, C minus B, right? Just check. B square minus BC. You are putting A equal to negative B. B plus C. A is negative B, so BC. And this is C square minus AB. So C square. A is negative B, so C square plus B square. And A is negative B, so this becomes 0. This anyway becomes 0, right? This is negative B plus B. So this terms becomes 0. And what about this one? What about this one? P of minus B. What about this one? Do you see something that it is happening? Something is happening or not? So suppose I take common. So suppose I write this is B times B minus C. So B times B square minus C square. Here I will take common B again. So B times B plus C and C minus B. We are there now. You see? We are there. Because now what will happen, that I am writing B times B square minus C square, and this is negative of B square minus C square. That becomes 0. That is just 0, right? This is 0. So P of minus B is 0. It means that for this numerator, which I am calling P of A, so P of A, it vanishes at A equal to negative B, and so I will have A plus B as a factor. So this has got A plus B, this has got A plus B as a factor, this has got A plus B as a factor. Similarly, it will have B plus C as a factor and C plus A as a factor. You agree this one? That this kind of thing? Just check. But then the catch is this, that what? This we expect, right? But then the constant also will be there, right? There is some constant also, lambda, right? So what I do, that this is P of A is 0, P of minus B is 0. Similarly, see P of minus C. P of minus C is also 0. Check P of minus C. P of minus C also will be 0. P of minus C. You just permute B and C. Okay. But wait, it is surprising answer. We cannot conclude this one so fast, right? Because people make a mistake, so I'm warning you, right? The people make a mistake that A plus B plus C plus A, and they think like that, okay, the answer is something, some different thing, something, but no, not really. Say, for example, if you put A, B, C all 1, 1, 1, suppose you put all 1, 1, 1, what is the answer? Obviously, answer is 0, right? So what is happening here? So this is P of minus C is 0, and here you have got P of, this is 0, P of minus C 0, P of minus B. And what about P of 0? Just calculate P of 0. Means if A is 0. If A is 0, then let's look at this expression again. This was my P of A. So A is 0, so you will get minus BC, B plus C. That's fine. This is 0. A 0 goes out, so plus B square C. And plus C square. And this all are 0, so plus C square B. You find this is also 0. Check that P of 0 is 0. Correct? So see, here is a polynomial in A, so call it P of A, which vanishes at minus B, minus C and 0. Means this polynomial becomes 0 at B, C and 0 itself. That means that this polynomial must be vanishing everywhere. Why? Because notice its degree. The degree is 2, right? This is A squared, degree 2. Here, A and A, degree 2. Here also, C squared is AB, A degree 2. So it's a second degree polynomial in A. It's a beautiful idea. So it's a polynomial in second degree A. So P of A. So polynomial of degree 2. But it vanishes at 3 points. And those points, I have to little add this one, that those must be distinct. That I can easily achieve. I can give you that B and C are different. And I can give you that B and C are not 0 also, right? Okay, I'll write in red. Okay, last right corner. Okay, good. So let me write again. So this is this one, that this is, I'm writing again here. So I am evaluating this polynomial. This polynomial is numerator, this P of A, my definition of P of A. Evaluate this at 0. So P of 0, you will find P of 0 to be 0. Because P of 0, if you put 0, see A is 0. So you'll get negative BC times B plus C. Plus this is B squared, and see this is 0. So B squared, and then you are getting the B squared C, and A is 0 again here. So plus C squared B. So it is BC B plus C. So you find that P of 0 is 0, right? So P of A polynomial, and if you put A equal to negative B, or A equal to negative C, or A equal to 0, then you are getting all different. I just have to give this one, that B and C are different from 0. I just have to give this number, that B and C are different from 0. Correct? Then just as to make the problem accurate. Otherwise what will happen, that you may say they are not distinct. So I just want that they are distinct. So B and C are not equal, and of course different from 0 also. Correct? So then I will get that, of course, this is true. Right? So those things can be always taken care of. So this is a good problem. And why have I have chosen this? Because it seems like that many people may mark 1 as the answer. Many people may mark 1 as the answer. If they are not very alert, they may mark. So please check yourself, guard yourself against that. Let me go to the next one. A tricky problem. Now this one. If A, B, C are real numbers, of course, real numbers, if I don't see anything, real numbers, such that the sum of them equals 1, sum of 3 fractions equals 1, then prove that 2 of them must be equal to plus 1 and third equal to negative 1. They are saying 2 of them must equal. So here you have got, this is some fraction P plus Q plus R 0. Final answer is, Arpita, final answer is 0. Right? Because I told you here that this is, people may confuse, but then here you see, even you put 1, 1, 1, you will find this one. But anyway, even you put differently also, you will get this answer. So the idea is that there is a polynomial P in A. It vanishes for 3 distinct values, and so I expected someone to jump, like Satvik is saying that cosine rule. Satvik, good that you have got good pair of eyes. You have got really good pair of eyes that you discovered and you spotted this one. But then that's half the story. Why it is not a case of cosine rule? Can someone quickly say? Like Arpita also is saying, oh yes. But I would say, oh no. You also fell for the trap. ABCR, they are what? Are they given to be positive? No, not really. Right? So I can't apply cosine rule. Are you getting my idea? So if someone who applies cosine rule here in a subjective exam like ISI or other thing, of course he won't get credit, right? Of course it will be unfortunate because it really looks like of course cosine rule, but then you can't apply because ABC are not given to be positive. Neither can you deduce that ABC are positive. Are you getting my point? It is not given, it is neither given, and yes, they can be negative, correct? Nothing has been given. And moreover, you cannot deduce also that they positive. Suppose not given, but somebody can deduce. Here you can't deduce also, and so no. So of course you can't apply. You will just heave a sigh of uneasiness that, oh, just if it were given, it was a beautiful solution. So that, like that. Okay. So let me come to that one. So it's like sum of three fractions and p plus q. This is not 0. This is given to be 1. And then we want to deduce something from it. I will do a super duper thing. What I'll do, this is, see, they're saying that prove that two of them must be equal to plus 1 and third minus 1. And this one is there. What I write, I'll write here this as p minus 1. This is my p minus 1, q minus 1 plus r plus 1. And if this, I can write 1. Do you agree this? It still does not change. R plus 1. So there will be 0 in fact. That is 0. I can write like this. So give two negatives here. Give one negative 1 to P, one negative 1 to Q, but then to R you give positive 1. Right? So that the balance is correct. This must be 1. So it transposes, it goes 1. Is that right? All of you? So I absorb negative sign, two negatives, in one in P, one in Q, and R I give a positive number, so R plus 1. Now, that's really interesting. Now, lot of factorizations occurred. I write b square plus c square minus a square over 2bc minus 1. This one. First, let me factorize this one. This one, only this one. This factorizes as, this is p minus 1, right? P minus 1, this one. So I can write b square plus c square. It is rich in factorization, minus 2bc over 2bc. So I can combine this with this. So I'll get b minus c squared minus a square over 2bc. That's fine. I can apply difference of squares. And so I'll get b minus c plus a. And this is b minus c minus a over 2bc. That's a good one. This is this. Again q minus 1. So I'll write c square plus a square minus b square over 2ca. So now this will happen. This is b minus c. Not this is b minus c plus a, b minus c minus a. That's right. That's correct. That's correct, Arpita. So that is this one. Similarly, if you write c square, a square minus b square, this one, and this minus 1, this minus 1. So of course you understand again that c minus a will come right now. So you will get c minus a minus b, c minus l at plus, c minus a plus b, c minus a minus b, and over 2c. This is what you will get here for the first one. Because just like this one, this comes this also. But the next one is plus 1, next one is plus 1, next one is plus 1. So beware. A square plus b square minus c square over 2ab plus 1. So now it is a plus b whole squared. So you will get a plus b plus c, and you will get a plus b minus c, and over twice ab. This is what we get by this kind of thing. So you see, if you notice, you can write this as negative of, right? Negative of, and just change the sign. So write better at a plus b minus c, a plus b minus c. This one, a plus b minus c. This is, and here I'll take common. So c plus a minus b, c plus a minus b over 2bc. This I'll write as negative, and I can write b plus c minus a. This I leave. b plus c minus a, and here I write a plus b minus c and over 2ca. I just have to add all of them because you have to add these three numbers. All these three have to add. Is that clear till now? I just have to add these numbers. These three expressions I have to add. I spot a common. I spot a common. What is that? See, if you notice closely, you will see that a plus b minus c is common to each of them. A plus b minus c, a plus b minus c, a plus b minus c is common to all of them. So I can write this. So let me write on the next page, and then I have to keep coming here also so that I can just write this one. So I will add a page. So I'll use a plus b minus c. This is common throughout, and upon 2abc. This also let me put. So I will write this one. So this is a plus b minus c upon 2abc. Now here you see this is minus a, so you will get minus of a and times c plus a minus b, c plus a minus b. Then here it is negative of b and b plus c minus a, negative of b and b plus c minus a, and here plus c and times a plus b plus c, c and times a plus b plus c, and this equals 0 because you are saying that this all is here. So we got this kind of thing, negative of this. So negative, we have got two negatives and one positive here, two negative and one positive here. Now if you closely see this, what do you expect? You expect that if a plus b minus c has come, look at this one. I had a choice. I could have also written this as, I could have written this as this. I could have played like this also. I could have written p plus 1. I could have written q minus 1 plus r minus 1 equal to 1. This also I could have equal to 0. This also I could have done. So I mean that what will happen, that once you have got a plus b minus c as a factor, you will find that the other factor also will come up, right? This means that you will have got, when you do it, you will get a plus b minus c, b plus c minus a, and c plus a minus b equals 0. You will get this all 0, right? Is that clear? You will get this product of these three numbers is 0. This is what you will get. Once you get that, because things are of course cyclic, right? So you will get that. So it means that a plus b is c, or b plus c is a, or c plus a is b. So it means that at least one of the numbers is some of the other two. So let's take the case a plus b equal to c. A plus b equal to c case. Other cases are similar. If this is the case, a plus b c, then now if you come here, you understand that if you will take this one, then one of them, right? You have to prove that two of them must be equal to plus 1 and the other equal to negative 1. So that will happen, right? Because two of them, p and q, will be plus 1, and next will be, because you are taking that one, right, are equal to 0. Is it clear? The third equal to negative 1, because we have taken like this. So now if the moment you see that this is 0, see, if a plus b is c, a plus b minus c, right? So you will get that, or you can directly check also, like a plus b minus c. For example, you want to test about b square c square minus a square over 2bc if a plus b is c. A plus b is c. So best would be that you derive the case on bc is already here, so you derive the case on a. So you write here a is c minus b. You write a as c minus b. So you will write here b square plus c square minus c minus b square upon 2bc. So you see, you will get b square plus c square, and see this is negative c square, negative c square, negative b square, and plus 2bc, and over 2bc. So of course this cancels, and you just get 1. So you will get 2 as, you will get 2, and then other things also you will get. Okay, is that clear? Yes. Is there some technical snag or something? Can someone just say that if there is some technical snag? Yes. So I want someone to say yes or no, because is there some technical snag or all right? All right. Then I will go to the next one. Okay, all right, that's all right. But then I am live, right? Okay, perfect. So let's go to the next one. Next one is this one. Simplify the following expression. It is a minus b, a plus b, and all those numbers are there. Here I'll follow a different approach. Although I can do by the other thing also, but here best would be that I'll write here. So b minus c by b plus c you take as x. C minus a by c plus a you take as y, and a minus b by a plus b you take as z. So x, y, and g. This is a lovely question. Now it will happen that because it is like this, what I can write, that I can use component dividendo, and I will get here, I'll just add them up. So I'll get 2b, or if I write b plus c over b minus c, I'm getting 1 over x. So I can use from here that b plus c, so b over c, I am adding and subtracting. So you will get 1 plus x and 1 minus x. So I hope this is clear. Yeah, component dividendo, correct. I'm writing component dividendo. So I get this one, b plus c over b by c is 1 plus x over 1 minus x. Now, similarly, I can play with other thing. Like c over a is 1 plus y over 1 minus y, and a over b is 1 over 1 plus g times 1 minus g. These things are coming up. Now this thing becomes x plus, so the thing here is becoming x plus y plus z. That's all right. And plus here you have got a minus b by a plus b. So this is x, y, g. I want to find this value. Now I want to find this value. Means I want to eliminate a, b, and c. That was the meaning was, right? So just if you multiply them out, you will get 1 plus x times 1 plus y times 1 plus g equals 1 minus x times 1 minus y times 1 minus g. Expand this one. So you will get 1 plus x plus y plus g plus, like symmetric function, xy expression, xy plus yg plus gx, and plus xyg. Here we will get 1 minus x plus y plus g plus xy plus yg plus gx and negative xyg. So I mean 1 cancels, xy plus yg plus gx cancels. What do you remain with twice of? So you are getting twice of x plus y plus g plus xyg equals 0. And so this gives you very nicely that this x plus y plus g plus xyg equals 0. Is that clear? Is that okay? That we get this as 0. This is a good problem. Something like this came in RMO, not RMO, I think maybe INMO long back, maybe 90, 91 or something. Something that was best on this kind of thing. That you do this kind of manipulation, that you do component dividendo, and then you just would notice that this produces, this is x plus y plus g, and you model the problem as that if I take this as a new variable, then if I eliminate a, b, and c, then whatever I get must have something to do with this expression, right? That's what I'm saying. Are you getting my point, what I'm saying? That you model it like that if I rename x, y, g, then because a, b, c I can eliminate, so I will end up with an equation in x, y, and g, and in that equation only I will get up this kind of x plus y plus g plus x, y, g is 0. Okay, got my idea? So this is what we'll get this kind of thing. Okay, let me go to the next one. This is 1 over a minus b, a minus b minus c. Something similar I had done last time, but then many people told to give more entries of this type. So I'm coming up with this one, a minus b, a minus c. So what is happening here is that see, there are 3 variables, right? A, B, C, and A is also there. So what should I do? I'll do like this. One I will do first. One approach is that I can think of three variables only, A, B, and C. So I know my model that A square over A minus B, A minus C, or A cube. These things are known to me, right? These things are known to me. Let's see that whether I can write this with change of variable. So I'll write here 1 by A minus B, A minus C. This I will transform as, I want to work with A, B, and C. So I want to work with 1 by A, 1 by B, 1 by C. What I write, that I take 1 by A and I divide by AB. So I will take AB out. So this is 1 by A minus 1 by B, negative I will write. And again I will take AC out. So 1 by A minus 1 by C, and AC negative, so this is positive. So this is this kind of thing. So let me put just here. So see, there are 3A cubed, right? 3A cubed. So it is 1 over A cubed BC, and you have got 1 by A minus 1 by B and 1 by A minus 1 by C. Although I should write AB, BC, CA, but this is fair enough, 1 by A minus 1B. Now what I get, if this is A cube BC, ABC I will write ABC here. ABC depends on just leave. Here you will get 1 by A squared and over 1 by A minus 1 by B and times 1 by A minus 1 by C. I think this is pretty good then. This you get. So 1 by ABC is throughout common. So if I write this sigma, then you notice that this expression 1, this sigma of three variables, sigma, that equals 1 by ABC and times you have got 1 by A squared over 1 by A minus 1 by B, 1 by A minus 1 by C. Let me write a couple of more terms. 1 by B squared over 1 by B minus 1 by C, 1 by B minus 1 by, I write A first, 1 by C, like this. Three terms. So it is like this one. Next, let me write the next one. This is like x square. I'm using this one, x square upon x minus y, x minus g, y square upon y minus x, y minus g, g square by g minus x, g minus y. This one. You know that this is 1. You know this is 1. This I did in last class. This comes of a consequence sigma x square times y minus g, that is negative of x minus y, y minus g, and g minus x. This comes because of this. So we know that pretty easily that it will come. Okay, so this is what we do: x minus y, y minus g, g minus x. So now if you apply this here, you see this is not in ABC but 1 over A, 1 over B, 1 over C. So this is 1 by A squared. So this all thing will be 1 by ABC, and time this whole thing will be 1. So your answer final will be 1 over ABC. 1 over ABC. This is your final answer, 1 over ABC. Is that clear? This is first method. There can be a third method also. There can be a second method also. So this is first solution. So I'm thinking of just three numbers A, B, and C. Three numbers A, B, and C. I'm forming cyclic identities in 1 over A, 1 over B, 1 over C, because this 1 by A is there. There can be a second method which is very elegant and tells you, this also is very smart. So other is this, that you have got 1 over A minus B, A minus C, plus 1 over B. Is that clear, everybody? Plus 1 over C, C minus A, C minus B. 1 over C, C minus A, C minus B, like that. Right? Now what I do, that I will take three variables A, B, C, and 0. A, B, C, and 0. I'm applying this rule. There is one identity like this. If you've got numbers as say numbers, take numbers at x, y, g, w, x, y, g, w. So I can write as x over or x square or whatever. So x square, x that we will take later. So x square over x minus y, anything x to the power k, you write x minus y, x minus g, x minus w, y g w, plus y to the k over y minus x, y minus g, y minus w, then z to the power k over g minus x, g minus y, g minus w, plus w to the power k, w minus x, w minus y, and w minus g. This expression I want, right? This is for k. This is for k. This is for k. So you will find that, call it sk. So you will find that s0 is 0, s1 is also 0, s2 also is 0, but s3 is 1. S3 is 1 because 4 variables, s3 is 1. For 3 variables, s2 onwards it was 1, and then other things will coming. So this is what we will use here. So I will use it for these variable. So I will write the for k equal to 0 case, means that's case when 0 will come. So this will give me that 1 over an a. So a, b, c, and 0. So I will write 1 over a minus b, a minus c, a minus 0. A is the first one, subtract. Then plus 1 over from b. So b minus a, b minus c, b minus 0, plus 1 over c minus a, c minus b, c minus 0, plus 1 over 0 minus a, 0 minus b, 0 minus c equal to 0. If I expand that, what I get? If I expand that, I'm getting 1 over a minus b, a minus c times a, see here, then 1 over b, b minus a, b minus c, plus 1 over c, c minus a, c minus b, and this is 3 negative, so negative 1 by abc is 0, which when bring to the other side gives the answer as 1 over abc. So that's a nice approach again. Okay, so this is what we will do, and we are getting. So this is one thing. Is that clear? Is that clear that what we are getting? So we get this one. So we get this as 0. So we get the 0, and then from we transferred we'll get ABC. So this is also good. Both are good solutions. One speaks of 3 variable, other is of 4 variables, and then interestingly this is much more, this is trickier, much trickier, because zeros you have to invent 0, right, which is not seen here. And then we got, if you do the other thing for same thing, you should get a similar thing, because here also you have got, if you check here, you have got here a squared, you have got here a square, a minus b, a minus c, b a square, b minus a, b minus c, and c a square. So again we will get the same thing. Okay. This answer, this I will just express, and we'll tell you that what you're getting. If you have got the next, the other one was 1 by a square, 1 by a square. This was part B. 1 by a square, a minus b, a minus c, plus 1 by b square, b minus a, b minus c, plus 1 by c square, c minus a, 1 by c squared, 1 by c squared, c minus a, c minus b. This we have to simplify, c minus b, this one. So now this is actually same thing, that I will simplify the first term. So I write first term as 1 over a squared, a minus b. I write the first term as 1 over a square, a minus b, a minus c. Again take ab out, so I can write 1 by a square, and you take ab out, you have got 1 by a minus 1 by b, and this is 1 by a minus 1 by c. So obviously sign, you will check the sign. So sign is like, this is b minus a, and this is c minus a, so both negative, gone. So ab has come and ac has come, so a square ab. So you'll get a to the power 4, or a to the power cube is better, because you'll get 1 over a to the cube and this is 1 over a b c, and here you will get interesting thing now. Last time you got a square, this time you are getting 1 by a cubed over 1 by a minus 1 by b, 1 by a minus 1 by c, and 3 more terms, just like this one. So this time it is time to apply. Last time we applied a square upon a minus b, a minus c, plus b square upon b minus c, b minus a, and plus c square by c minus a, c minus b. We applied, this was 1. This was 1 we applied last time. Right, this was 1. What about a cubed? If I write a cubed by a minus b, a minus c, plus b cubed by b minus c, b minus a, and plus c cubed by c minus a, c minus b. That is now a plus b plus c. This is not 1. This is now a plus b plus c. So you will get here. So this is here. So from here you should get the answer as 1 by abc, and this is same identity but applies with 1 by a, 1 by 1 by c. Is that clear? It is the same identity. This is very famous identity, but now applied with numbers not a, b, c, but numbers 1 over a, 1 over b, 1 over c. So 1 by abc, 1 over a, plus 1 over b, plus 1 over c. You can simplify it also. So this is the answer we'll get. Means we'll get ab plus bc plus ca, and over abc whole square. Easily I can give you something that abc are roots of some equation, and then you want this number. So that will be a good question. abc are roots of this equation, and find this one. So is that clear to you, all of you? Challenging problem, tough problem. You must love these challenges. They are one of the best in cyclic identities. Okay. Just the one that I told right now, that ak over a minus b minus c, and x minus a, and all these numbers. So this, you see, for k equal to 1, 2 only you want k equal to 1, 2 only, right? Again, follow the same thing that I did this way, that if you write sk, there are 3 variables. See, x has come up, right? So I will write like this. If I can write s of k, if I write sk, yes, sometimes little lag is there. Yes, Chris, you are right that sometimes this little lag is there because of some technical glitch or something. But I hope it's in limits, right? So s of k, if I define as a to the k over a minus b, a minus c, a minus d, plus b to the power k over b minus a, b minus c, b minus d, plus c to the power k over c minus a, c minus b, c minus d, plus d to the power k over d minus a, d minus b, d minus c, and this will be 0 for k equal to 1 and 2. That's what we learned for k equal to 1 and 2. In fact, S0, S1, S2 all are 0 till here 0, 1 and 2. So they also want for k equal to 1 and 2 only. But then this answer is not 0 because you have got 3 terms here, you have got 4 terms. The trick lies in that apply this expression, apply this identity for numbers a, b, c, and x. A, b, c, and x means d becomes x. D become x. So I'll write a to the k over a minus b, a minus c, a minus x. Be patient and be slow. So b to the power k, because it's algebra, if you make a mistake you are lost. B minus c, b minus x, plus c to the power k over c minus a, c minus b, c minus x, plus x to the power k over x minus a, x minus b, x minus c equal to 0. This one. Now I can just change the sign of here. This all sign I can change. I can write this as a to the k. I will write this as a to the k over a minus b, a minus c, and I can write x minus a, this negative sign, again b to the k over b minus a, b minus c, x minus b, plus c to the power k over c minus a, c minus b, x minus c. I get x minus c, so c minus a, c to the k over c minus a times c minus b times x minus c, and here so all signs are changed, so here I will get the other side, this one. So this is just everything is negative, so x minus a, x minus b, x minus c. So we get this one. So if it is square, then if it is k equal to 2, for k equal to 2, for equal to 2, your answer will be x square. Good answer, x square by x minus a, x minus b, x minus c. It also something called partial fraction. You can check it is partial fraction, which is used in integration. Same thing you would have done in integration also. But the idea comes from splitting into partial fractions. That is algebra thing, nothing to do with calculus. It is a tool used many places. So that is one. Let me go to the next one. Any doubt till here? Any doubt till here? Anybody any doubt? One by a minus b, a minus c, x minus a. This is also same thing. 1 by a minus b minus c. So I can choose my variable as a, b, c, x, right? I can choose my variable as a, b, c, and x, 4 things. So 1 upon a minus b, a minus c, a minus x, plus 1 over b minus a, b minus c, b minus x, plus 1 over c minus a, c minus b, c minus x, plus 1 over x minus a, x minus b, x minus c equal to 0. And then if you change the sign, so I can change the sign and I can bring this side, so I can get 1 by a minus b, a minus c times x minus a, plus 1 by b minus c, b minus a times x minus b, and other x minus c equal to 0, right? Not 0, equal to this one, equal to this one, that 1 upon equals 1 upon x minus a, x minus b, x minus c. Correct. In fact, what happens is this, that if you do in class 12 something called partial fractions, there you will study partial fractions, that if you do partial, you have to express 1 by x minus a, if you have to express 1 by x minus a, x minus b, so if you have to express 1 by x minus a, x minus b, x minus c, this you have to express in terms of partial fraction. Is that clear, all of you? Partial fraction. Let me refresh this. So it is partial fraction. If I expand, then I will get here capital A constant, a over x minus, I choose to write a, capital B over x minus b, and c over x minus c. And the heavy side cover up rule. Heavy side cover up rule gives you, if you want to find a, then you just put here x equal to a, ignoring this, but it is 0. So you'll get 1 by a minus b, a minus c. So you will get 1 by a minus b, a minus c. Again, x equal to b. So this is a. Your b will be 1 by b minus a, b minus c. And your c will be 1 by c minus a, c minus b. I hope this is the same thing. Just to check the calculation, it will be same thing. Is that clear? So this is what you will get. It is partial fraction also. By the way, if you have to integrate this thing, you will of course use this only. So these are just the tools, how it works and what it works, that you can do always later. All right, students, all right, children. I hope all are clear. This also is same thing. It is just x plus a is there, so that I don't care much about. So I can write this as a square. First I can write this as a square by a minus b, a minus b, a minus c, a minus y. I can write this as a square over, I can write this as a square by a minus b, a minus c, and then x plus a, this one. So I can write this as, just write this as a squared, just as I love negatives here, so a squared by a minus b, a minus c, and write as a minus y, and take y equal to minus x, take y equal to negative x. It may help you to see it in a good light, because y equal to negative x. Now what will happen? Now it will happen that this will rewrite as a square by a minus b, a minus c, times a minus y, plus b square by b minus a, b minus c, b minus y, plus c square by c minus a, c minus b, c minus y. Now this is going to be 1, right? This is not okay, not 1. C square by c minus y, c square by that we did just last time. C minus a, c minus b, c minus y. That we did just last time. Y. Check this one. X square over, right? We did here. Check here. We did here 1 by b minus a is this one. Then we did here also. This was x square by x plus x minus c. So this is y square over y minus c, this one, and y equal to minus x, so it is x square by y equal to minus x, so we'll get x plus a, x plus b, x plus c, this one. So this kind of thing we'll get. So basically it is coming from the same identity. Is that clear? Yes, any doubt here? This is one tough problem. A to a squared, a plus b, and some bit new idea. Can someone tell? Can someone just tell for a minute what he will think? Yes, so this looks quite messy and quite big. A square times a plus b, a plus c, and b square times b plus c, b plus a, and again c square times same thing, and upon these things c minus c minus b. So how will you get it? Is there a shortcut to it? Got it? So can you explain that? Someone called Graph is God. So can you explain how you got it for the benefit of the audience? Just a quick line from you that will convince us that yes, you do seem to have got this question. Some fine argument. See, I will do like this. I will expand. I will write this as, of course, a minus b. I'll take LCM a minus b, b minus c. It is a good question. C minus a. Now a minus b is all right. B minus c and c minus. So c minus a is there. You will get negative throughout, right? This is clear, right? Because a minus b and a minus c, so negative minus c. B minus c, b minus a, so negative, and then this one. So we'll get minus a square. I'll write first minus a square, a plus b, a plus c. This is b minus c. I'm getting b minus c, right? A minus b, b minus c, c minus a. So a square b minus c. So now let's play, and then 3 more terms like this. Let me play with this one. A square times a plus b. That looks quite ugly, quite bad. A plus c, b minus c, quite big. But then, not all is lost. I can write this as a square, and notice here, expand this one, you will get a squared plus b plus ca plus bc, and then times b minus c, right? So I can write a squared, and this you can play in 2 ways. So what you can write here is that you can take a common, you will get a times a plus b plus c and plus bc times b minus c plus bc times b minus c. That is a squared, that is a cube, a plus b plus c, b minus c plus a square bc, b minus c. This I am writing. If you are clear, you can check that this is what I am writing. If I take sigma, so if I take sigma, say suppose I take sigma means 3 terms, I say take sigma a cubed. If I take sigma a cubed, a plus b plus c, b minus c plus sigma abc, a times b minus c, then you see that this will give you a plus b plus c is common, that comes out here. This is sigma a cubed b minus c minus bc is out, sigma a squared bc is out minus bc is out, or a square bc, no, bc is out, minus bc is out, minus abc is out, and sigma a times b minus c, right? So sigma a times b minus c is 0 only. This is anyway 0. This is anyway 0, that we know, correct? A sigma a times b minus c, because abc is common. Just check it once. A square, a plus b, so I got a square. This is a to the power 4, no. A square is b plus c a plus bc, so I can take a common. So a times a plus b plus c plus bc, b minus c. So I got a cubed, this one, b minus c plus a square bc, b minus c. So I can take abc common, and we got this one. So plus abc, b minus c. This is plus abc, so plus. Now here, sigma a cube b minus c and a plus b plus c. A plus b plus c. This I can evaluate. This I can evaluate, right? Sigma a cube b minus c I know. So let me write the next one. So sigma a cubed b minus c. Sigma a cubed b minus c is, we know is that this is negative of a minus b, b minus c, c minus a, and times, now a square was a square. If you write sigma a square b minus c, remember sigma b minus c, that was you have got negative of a minus b, b minus c, and c minus a. But a cube is not this. So this will be this a cube minus c, and then here you have got a plus b plus c. That's what you will get, a plus b plus c. So come to the next page, come to the previous page. If it's this one, this is element common, this we want, and this also is there. This is negative 1. So I'll get this numerator. I'll get this numerator as a minus b, b minus c, c minus a, and times a plus b plus c whole squared, right? Because a plus b plus c is already common here, and if you remember, one a plus b plus c was here also, so that pretty much seals it. So you will get that one, correct? So is that clear? You will get this. Okay. In fact, we can also get an expression like this one, that a to the power m if I write sigma m is like a to the power m a plus b a plus c over a minus b a minus c a minus b a minus c plus b to the power m b to the power m b minus a b minus c by c minus a b minus a b plus a, everything is plus b to the power m. This is b plus a and c plus a, just like we got a plus b plus c, so b plus a and b plus c, b plus a and b plus c, and upon b minus a and b minus c, and then c to the power m c plus a c plus b upon c minus a c minus b. This one. This also we can do similarly, a b b c c a. Is that clear? That this also I can use recurrence, because once you expand a to the power m and a plus b a plus c, that is a to the power m a square plus b plus c times a plus bc. So we'll get a to the power m plus 2 plus b plus c a plus b plus c is actually, so it is actually a to the power m, and this is a times a plus b plus c plus 1 plus bc, this one. So I will write that a to the power, I will write that a plus b plus c is out, so I can write a plus b plus c. I hope this is clear to you. A to the power m plus 1 and plus abc plus abc, and this is am, so this is abc and sigma a to the power m minus 1, like that. So I can again write all these numbers, so I'll get the answer a plus b plus c whole square as usual. So this is about this one. Let me go to the next one. This again is the same idea, a minus b, a square b square minus c square, and then other thing. So how do you think this will play out? Like what somebody can do, and what is the answer maybe? Can someone give this some idea that how you will get this idea? A minus b, a square b square minus c square. If you expand completely, brutal expansion, that will not be good. If you expand completely, introduce some symmetry, because if a sum depends on ABC all, then that comes out of the factor when you do sigma. So my approach is sigma only. So I'll consider sigma a minus b sigma a minus b a square b square minus c square times c square. This one. Anybody any idea? Very tricky problem, but if you look at it right way, it will be easy. Anybody any idea? They can tell. Yes. See, just like last time, no? Just like last time, that I expressed a plus b plus c as some number, no? A plus b plus c. So this I can do in many ways. Like even I could have done this also. Even that might not be good here, but a plus b a plus c I can write as this either, or I can write this as a square plus b plus c plus bc, right? And so I can write this as this also, a square plus bc plus ca plus ab. So depends on what I want to write it. I can have done anything. So do you have any idea about this, that how you will do? But here I chose differently. Here I chose to do like this. Here I chose that I will write like this. Let me record this for next one. That what I did is that I wrote a squared. I wrote a plus b a plus c in two ways. I can write either a times a plus b plus c plus bc, 4 terms, or this will be a squared n plus ab plus bc plus ca, this one. So a squared plus this, or a times this. So can you use that one? So this is a times ap plus bc pa, and this is a square plus q. Both have advantage, but then see, a square plus q, obviously degree is more, here degree is less. So this is preferable, degree is less. But we know many values also. Okay. Here there is no approach. So here I will write here, no direct approach. So I'll write here. Yes, anything? Yes, there is some little lag, right? I understand that there is little lag. Okay, so I can write this as a minus b times I can write a square b square c square minus 2c square and c square, right? So put a square plus b square plus c square equal to lambda. Welcome, Sivans. Please be regular in the class. You need to learn more things. Okay, so I put this as lambda because this depends on all ABC and lambda remains unchanged. Any doubt here? All right. Now, so this becomes a minus b and times lambda minus 2c square times 2c square. This one. So I get lambda times c square a minus b minus 2c to the power 4 a minus b, right? This one. This way your thing becomes easy, because now this is just a square b minus c, b square c minus a, c square a minus b. So now this becomes negative lambda a minus b, b minus c, c minus a. So negative lambda, this becomes negative lambda minus b, and this is minus of 2c4 minus b, so minus 2 and c4 minus b. So this becomes 2 times a minus b, b minus c, c minus a, c4 is there. So you know that this will become now a square b square c square plus ab bc ca. This one you will get this kind of thing. So now this will become a minus b, b minus c, c minus a is common. This is 2a square plus 2b square plus 2c square. This I get, and plus 2 sigma ab and minus a square b square c square. So this is a good thing actually. So I will get a minus b, b minus c and c minus a, and times a plus b plus c whole square. We get like this. Is that clear? Just check. It's a good expression. Just check the answer. A minus b minus c minus a times a plus c whole square. Really tricky, tough. Everything you can tell it. If you don't, if you can't find a way in exam, then of course you are doomed, because this expression just by multiplying it won't come. You have to have some method, some structure. This is the structure. This is the place. Cyclic thing is the place where I want it to all go away. Okay. Yeah, this is one inequality problem. So how do you attempt that? This inequality problem. Anyone can attempt inequality problem. Sum of 3 squares you have to give greater than or equal to 2. ABC are given pairwise distinctive numbers. That is of course true. So the things will be 0 and meaningless. So how do you want to start it? So how someone is going to start it? Any idea? Okay, I will use this one. I will use this one, that x square y square g square is x plus y plus g whole square minus 2xy minus 2xy plus yg plus gx. This one. So I can apply that thing here. I can apply that thing here. So I can say that a square by b minus c whole square, b square by c minus a whole square minus b whole square, that equals that this is whole square, that you don't leave this whole square, minus the interesting part, minus 2 times, and now you have to multiply. So you'll get ab upon b minus c minus a, this one, bc upon c minus a minus b, plus ca upon a minus b and b minus c, correct? This you will get. Okay, ab by b minus a, b minus c, ab by c, b minus c, and c minus a. So what you are getting here? Are you getting 1 here? Can you check that you are getting 1? Because you see, you are getting ab upon b minus c and c minus a and something. So you write, you will get ab a minus b, you will get ab a minus b, another thing, and sign will be negative here. So you know that this will become this thing, that plus 1, right? Because this is minus 1, so you will get plus 2. So look at this square, and this whole thing is negative 1, and so this is positive 1, so this is plus 2. So now we have proved that this is p, this expression p was to prove. So this p is some perfect square and plus 2, and so p greater than or equal to 2. You can also find where inequality occurs, that also I can find. Okay, be careful about sign, and be careful about this one, that sum of squares, of course, sum of squares comes from square of sum and minus 2 times product of cross terms. So like that, and that may be good sometime. It is here, it is really good. So we got the answer. Okay, this we have done the same way, a minus b, a plus b, a plus c. Okay, this is any doubt here? We are getting a plus b minus b. So what we can do is that same thing that I told you last time, that I can write again b plus c. That will be the best method. B plus c, b minus c is y. No, that is x. Let's name it at x. What is not present? X, c minus a, c plus a, c minus b, c plus a, c minus a equal to y, and then you will get bc, ca and ab. A plus b by a minus b is g. Like that you will get x, y and g. Again, complementary dividend will give you 1 plus x. I did something similar. So x plus and x minus 1 is b by c. Y plus 1, y minus 1 is c by a. Again, complementary dividend. So I will get y plus 1 upon y minus 1 is c by a, and here again something, you get g plus 1 with g minus I is g plus 1 over g minus I. G plus 1 over g minus I is a over b. If I multiply, I will get the answer. If I multiply, I will get 1 plus x, 1 plus y, 1 plus g equal to minus of x plus 1, y plus 1, g plus 1. This you will get, right? Now this you can expand, you will get the same thing. So this is 1 plus x, 1 plus y, and this is x minus y. So this I can write as 1 plus, this is this I can write as this one, or I can take negative out also, and I can write 1 minus x. That also will be all right. So 1 plus x, 1 plus y plus z is 1 plus sigma x plus sigma xy plus xyg this will be 1 plus sigma x sigma xy plus xyg, this one. And here it is negative, no, not negative, negative I can take out, I can negative is there, x minus 1, y minus 1, g minus 1. Okay, so negative is not there, but I can put a negative throughout, so I can write 1 minus, because in terms of that the equality to prove is xy plus yg plus gx equal to 1, something similar. So this is 1 plus sigma x this is 1 minus sigma x, this is plus sigma x. Here also you will have to expand, x minus 1 is there, so minus 1 could take minus 1 minus 1, and then 1 minus x, 1 minus 1 minus z, so 1 minus sigma x plus sigma y minus xyg, like that you will move. So you will get this as equal, just as if you remember you got the problem which was before. One problem you got, let me show you if you have forgotten, it was some INMO problem. So it was some problem where you have to prove that thing. No, let me check that once for you. Yeah, it was like this kind of thing, right? So you can check that later. Okay, next is one, factor the expression. Factor this expression, ab minus c square plus b minus c square plus c minus b whole square. What do you guess it to be? Any guesses that what it can be? Even if you don't know the answer, we can guess. What is that? Yes, guys, come up. I'll give you a break for a minute. See, if you expand directly, nothing useful you get, right? Just let's check this one, the first one. So this is a times b minus c whole square, b times b minus c whole square, and c minus b whole square plus 8abc. So I'll get a times b minus c whole square. If I expand, I will get a times b square minus 2bc plus c square. So I get like this, b square plus c square, a times, and minus 2abc, and again something similar. So minus 2abc. So let me expand that. This also is important, but not so much. Yeah, Manav, correct. Yes. Perfect, Manav, perfect. Lovely, good solution. Yes. So this is minus 2abc. So if I write sigma a times b minus c square, all three terms, I will get a times b square plus c square plus b times c square plus a square plus c times a square plus b square minus 6abc and plus 8abc. So I'm getting a times b square plus c square, b times c square plus a square, and plus 2abc. And c times, of course, a square plus b square plus c times a square plus b square and plus 2abc, 8 minus 6. So you will get, of course, a plus c, b plus c, c plus a. So how you will get that is this way, that there is one identity that I can relate here. This identity is, I will just write on the next page. A plus b, b plus c, c plus a. That happens to be a plus b plus c times ab plus bc plus ca minus abc. This is what it happens to be, right? And let me expand this and show you that what this means. A plus B plus C and AB plus BC plus CA. So this number is, if you multiply, see, you will get, if you multiply A, so you will get A square B plus C, you will get A square, you expect 9 terms, A square B plus C, B square C plus A plus C square A plus B, and then you expect 3ABC. So 3ABC, A square B plus C, B square C plus A. If I put it here, I will get here that A plus B, B plus C, C plus A is A square B plus C plus B square C plus A plus C square A plus B, and plus 3ABC. So plus 3ABC minus ABC. So A square B plus C plus B square C plus A plus C square A plus B, and this is plus 2ABC. So this is one factorization that we should learn, and I will box it so that you will remember for future use. You will write A square B plus C plus B square C plus A and plus C square A plus B and plus 2ABC, that will in fact become A plus B, B plus C and C plus A. You can check here that ABC will come twice, right? Because for ABC you need to have, you will get one A from here, one B, one plus C here, or you will get ABC or BCA. It will give you 2 ABC. Other thing, A square B plus C, you understand, you will get A square B plus C, B square C plus A, because A square B you will get A square B will get, why? Because you will get A here, A, and then A and B, A square B, then you will get B square A also, right? So this, I write like this either, or you write like this one, that AB times A plus B, both are same thing, BC times B plus C plus 3A plus C times A is this one. So if you do this, then it will become easy and you get the correct answer that people said, A plus C plus C plus A. Even this also is same, because here you can easily transform it to the other form. If you see, this is 8 ABC, difference is C, A plus B plus C square, I write A B minus C square, or I write